So I just want to talk a bit about my experiences doing some mutation testing on a small to medium-sized block. There's been a couple of those that we've done, myself and Jim. They've been verified formally, and yeah, just talking about the mutation testing of that. So when you're property checking, as I think Lawrence put almost exactly the same slide up, there's two big problems. Are your properties complete? Have you got a property for every part of the design? And are your constraints, are you over constraining? Are you stopping testing of valid scenarios? And really that was the motivation for using mutation testing to basically test these two points. So if you've got a design block, and if you're the person who's actually having to sign it off before it goes to be made into a mask set, you want to be pretty sure that it's right. So you make sure that you've done all the tests on the test plan, you make sure you get your functional coverage, and you make sure you've got your structural coverage, your branch and expression coverage, as you all know. For formally verified blocks, though, you don't really get your branch and expression coverage, and although lots of EDA companies try to get something vaguely equivalent to it, if I'm signing it, I am not at the moment comfortable signing off just on a formal verification on the coverage that you get from formal. So usually what I would do is I'd make sure that there is an additional dynamic simulation environment that you can get the structural coverage from your branch coverage and your expression coverage. And obviously this takes extra engineering effort to create the test bench and the test that you don't really need because you've completely verified this block formally. And I think the fact that you need to also have the dynamic simulation environment as well as the formal stops the property checking from being a standalone verification technology, because you kind of always need both of them together if you're going to, well, I certainly I'm not going to sign it off without the information from the coverage information from the dynamic simulation. So an objective, part of the objective of doing this mutation testing was to see if we were able to sign off a design that was completely formally verified without the need for the extra coverage that we'd have got from dynamic simulations. And it's also, I think, important to note that frankly, expression coverage and branch coverage isn't a very high bar to meet. It does not mean, if you've got 100% expression coverage, it doesn't mean that you've got no bugs in the design. Even if you have got your other, even if you have followed your test plan and got your functional coverage. So I think that there is a need for an improved coverage, structural coverage matrix, and I think that probably mutation testing does allow you it is an alternative that you could be using. So I think somebody else has just sort of mentioned this in another slide, but I will quickly go through it. What I mean by mutation testing. Basically, you're mutating, you're breaking your RTL. So you go through the whole RTL, and where you see things like an AND, then you replace that with an OR. If you have an if condition, you replace that with always being true, or always being false, or the opposite of the actual condition that you want. Also, whole statements are deleted. There's lots and lots of different ways that you can mutate. And what you do, you take an individual mutation, just one at a time, and then you run a full block regression on that. So basically, you run all your properties, and one of those should fail if you've verified correctly. Systematic mutation testing means that you go through every single mutation one at a time, and that's what I mean by getting coverage for structural coverage throughout the structure of the RTL. And I think that it's a better metric than purely expression and branch coverage, because you don't just require that bit of code has been executed. You require that a test has actually detected a failure in that point. So it's not just execution. Your verification environment test set. The mutation testing tools you can buy off the shelf ones, or it's relatively straightforward to do it in-house because you're just going through your RTL. You can parse your RTL and put in mutations pretty straightforwardly. If you want to systematically go through and check all your RTL, mutation test all your RTL with a dynamic simulation, that is going to take a long time because you've got to run your full regression for each mutation. But for formal, it might be possible. Basically, the key to this is you're looking for fails, not passes. So a big caveat here: if you've got a low state design, okay, so then your properties will fail. We found that almost all the properties failed within 10 seconds for each mutation. So even though the properties some of them take almost an hour to pass, they fail within 10 seconds. So you don't have to wait for the passes, and overnight you might get 20 mutations that were not detected at 10 seconds, that then you rerun the next day and they are detected. I was using 40 seconds or so. So how long does it take? As I say, our designs, they're not huge, they're not too small either, small to medium. For both the blocks that we were looking at, we had about 100 properties, and also about 5,000 mutations were identified. So 5,000 mutations times 100 properties times 10 seconds. You don't need to wait usually until the last property of your set of 100, so we can cut that down by 2. So it's basically 28 days is the amount of time it takes to run if you've got a single license. But if you have 28 licenses, that's just one day. And that is, I think, a very good coverage metric that you get for one day of processing. But it's not your full design, it's just one block. If you get a mutation that you've injected that has not been detected, what does that mean? So it either means that your property set is not complete, that you do not have a property that would pick up that bit of logic, that mutation, or you're over constraining. You're not testing part of your logic in a valid scenario. Or actually, we found redundant code. We found quite a lot of little bits of redundant code. Some of them you really do not think should be redundant, and they take a long time to analyze, and then you can eventually work out why they are non-detected. That did take a long time to convince ourselves that we really understood why these mutations were not detected. Some of them were much easier to realize that they are redundant code. And actually, we fed back quite a lot of, some of them quite significant, RTL optimizations that we didn't realize were possible to be made, but we found them through mutation testing. So the big question, can mutation testing replace traditional structural coverage? Well, in theory, yes. I think it's a much better metric. But of course, it is very computationally intensive and license intensive. I mean, I guess the EDA companies could change their licensing policies, and you might be able to use them for mutation testing only. Anyway, that's another matter. The problem is, though, that any RTL change you make, including perhaps latent modifications that you made as a result of your mutation testing, you want to retest those before you sign off on that. And unless you have an awful lot of machines and a lot of licenses, then, well, I wouldn't do it. So I would rely on the traditional methods. But if we could, there is the potentially engineering effort to be saved by not producing additional dynamic simulation environments. There is I think that one possible usage model that's worth considering is if you use mutation testing to prove that your set of properties are good. This is before final RTL, and then you can, if there's some minor RTL changes, then you can make some tweaks to your properties, but you assume that the property set is complete, that you are not over-constraining, and then you just rerun your properties on the final RTL, and then perhaps you could rerun full mutation testing after tape-out. Just my final summary. So mutation testing does find holes in property sets, and it does detect over-constraining. And it also identifies redundant RTL, which is a double-edged sword, actually. Key to it, though, is you gain confidence that your own properties are complete and they're good, and also any colleagues or any work that's being done for you is also complete and good. Okay.
Thank you. Any questions? Oh, there's quite a few questions.
Thank you, Anthony. Why do you need all 100 or even half of the properties failing? Wouldn't just one property failing be enough?
Sorry, I didn't make that clear. Yes, a single property failing. That's all you need. And so you run through the first property that fails, then you move on to the next mutation. Yeah. Sorry if that wasn't clear.
I have just a quick question about how do you manage the mutations? So is it a sort of flow? I mean, are you using off-the-shelf flows?
I can't give
any
information on that,
yeah.
But
okay, that's fine.
But yeah, go on.
About that. But it certainly sounds very valuable.
I think it is.
You have to get him drunk, I think he might. There was one more question, I think.
Okay, can we assume that you're only suggesting this is useful for the sort of cellular replacement structural coverage, and it's still not going to show up any missing functional coverage in terms of functionality? No. So I would implement your test plan. Yeah, you've got your test plan. You need to make sure that all your tests are done. Yeah, so you need to check your functionality. And the other thing I would ask is, in terms of amount of resource, I don't know what you're still using, but have you, how many times more equivalent to a normal football run have you had to run, would you say? Well, is it 5,000 in the bounds of that, or is it less? If you say it's under the assumption that you don't find a failure. So we ran with one license. We did find failures. You have to analyze those, but generally speaking, we've been running with a single license, running for about 3 weeks, basically. And how does that compare to your normal runtime for a? So the normal runtime to get passes, because that's not what we're doing. We're only trying to find fails. To get passes, somewhere between 12, 24 hours, something like that, to get full passes on 100 properties.
There's one question online, Anthony.
There's another one down here as well.
That's Systematically has got a question.
Okay, then I don't have a question. So, can we get a name of the tool?
No.
Thank you, Sasha.
Oh, Ian's got a question.
Keeping you exercise, Mike.
Yeah, when you talk about redundant code, is that not dead code? Are you talking about something, or is it another tool?
Okay, so this is quite interesting. There is a clear difference between redundant code and dead code. Dead code cannot be executed. So we found lots of code that could be executed, but actually wasn't used. There's a couple of reasons for it. Perhaps another piece of code does the same job, and a couple of pipe stage later they converge. So that's one situation. But we found, I guess, a handful of very weird situations where you think, if you delete that line, there is no way this can work. And actually, when you spend a lot of time analyzing it, it does work by 2 or 3 coincidences. I mean that actually, it works. You wouldn't update the RTL to get around that. You keep the RTL as it was.
Okay, and the online question is, do you use the flow late in the verification when most properties are written, or earlier in the flow as a guide to property development?
So I haven't used it an awful lot, so I haven't necessarily developed a perfectly shined way of using it. But no, wait after properties have been developed, then using it to show that that property set is correct.
Okay. Okay. Thanks.
Okay.